Welcome to the 10th lecture in Lattice Boltzmann methods, which unfortunately, due to some constraints, is also the last lecture, at least the last official one that we have in this semester, because it's the last day of the semester 2022-2023. And we finished this lecture with, of course, the most interesting thing about the Lattice Boltzmann method after, at least in my opinion, but I'm very, very biased. So after now learning about the multiple relaxation time method and about many things that don't really work in the multiple relaxation time method, we'll learn how to actually do it correctly. And this is using the Cumulant Lattice Boltzmann methods. Okay, there are not too many points here. We just want to talk about the transformation between raw and central moments. Oh, okay, come in. Just started with the. Okay, we'll just talk about the transformation between raw and central moments. Then we'll look at Galilean invariance and why this doesn't work with the usual MRT, and then in the end we come to cumulants. Okay, so let us begin with the conclusion that we had in the end of last lecture, and I hope you can see this. If don't, just come closer, yeah? This is the size of the screen that we have today. You're young, so you can see. Okay, the conclusion last time when we looked in 3 dimensions at the moment M211, we found that this will crash our MRT methods, either when we do it unweighted orthogonal or also when we made it non-orthogonal. Yeah. However, we could repair it by making it weighted orthogonal, and weighted orthogonal leads to the I didn't want to move this. Leads to the definition of the new moment, which I now call N211, being M211 minus theta M011. Yeah. So when we define this moment and we relax it, then this spurious coupling that was not present in BGK disappears also in the MRT. Now, the problem with this is okay, it is pretty ad hoc. Yeah, so we find that there's a problem, and if we can fiddle around with the moment, and then we get this moment, and then it works. But is this the only problem, or are there more problems of this kind? This is one thing. And another thing is whether the frame of reference matters. So this is something that we have not yet discussed, at least not in the last 4 lectures or so, and not in much detail. But what we have to notice by this definition of the moment is these raw moments are always taken in the resting frame of reference, so in the Eulerian frame of reference, which we also call the laboratory frame of reference, yeah, where we don't care about the movement of the fluid. And if we define the moments instead of in a moving frame of reference, the definition again will change. Yeah. So now the question is, this orthogonality that we now got in that particular frame of reference, will this hold in other frames of reference too? Yeah. So, and this is spoiler, this is not the case, but we have a solution for this. Okay, and today it's about the solution. So, frame of reference, we have to remind ourselves that the classical MRT uses these raw moments Ra moments, which means they are using the Eulerian. They are defined in an Eulerian frame, and this is, could also say this is a fixed frame. And now we can do this in a little bit a different way. There's also models that use central moments. We'll not discuss these moments in particular detail because they are like, what should I say? In German we say Durchgangstechnologie. Yeah? So it is something that solves half of the problem. Yeah, and so it was an idea that we had. Okay, we repair this problem this way, but then we still have the orthogonality problem. And in the end of the day, we want to have the orthogonality problem solved and the Galilean invariance or the frame problem solved both together, and then we then using central moments only uses half of the problem, and therefore this is not longer recommended nowadays, or at least most of the time. So central moments, I think we introduced central moments. These are moments taken in the Lagrangian, so this is the moving frame. The Lagrangian frame, so this is the moving frame, the frame moving with the material. Or you could say also, the material frame, probably is a better word. Okay, so how are they defined? We know now after 10 lectures, after 9 lectures, what are Ra moments, the Eulerians. The Eulerians, yeah, this is like a tribe, you could say, yeah. The Eulerians, they are, we write them with M just to distinguish from the others, and you remember this is the sum over now in 3 dimensions, I, J, and K. I by the power of A, J by the power of B, and K by the power of C, F, I, J, and K. And the central moments, we've not talked about them that much. Lagrange. So how do they look like? First of all, we need a different letter, and we just call them K for whatever reason. Yeah, K, A, B, C is now the sum over I, J, and K. So now the thing is the following. I, J, and K are the indices of the velocity, yeah, but in a fixed frame. And now we want to move this frame to the frame moving with the fluid, yeah. And this is done. So we have to move I, and we move I by subtracting UX and divide by, C. C is not the C that is written here, but C is the letter speed. So I write it a little bit different, and I'm running out of letters in this here. So we modify I in this way. We modify J, we subtract the Y velocity divided by this C, the power by B, and we modify UZ divided by C to the power of C, now which this C is that one here, and this, all of this times Fij K. Yeah, so this is the definition of the central moments, and by definition now, put it the other way around. So what is ux, uy, and uz? Ux, uy, and uz are the values that you obtain when you set these guys here to 0. So the first central moments are defined to be 0, right? And from the definition, first moments are 0, you obtain u, ux, uy, and uz. These are the ones that make this 0. Okay, so this is the moments centered. Therefore, the first order moments are obviously disappearing. Now there is lots of theory about central and raw moments. For example, you can transform central moments in raw moments and the other way around. And this is done by the binomial transform between frames of reference. So if you have the one moment, you can compute the other moments. If K, A, B, C is now can now be written like this. So these, okay, I have to announce, because I'm running a little bit out of letters, this I, J, K are not the I, J, K of the F that I'm now writing. Yeah, these are just indices. Yeah, but usually we start with I and then we J, J and so on. Yeah, so this I goes from 0 to A. This J is from 0 to B, and this K goes from 0 to C. And now we have here the binomials A over I, B over J, and C over K. And this goes into -1 by the power, so this is an ugly equation, A minus I plus B minus J plus C minus K. And all of this times, I write it in the next line, sorry for that, the moment Mij, so this is the previous moments, M100 divided by M000. I remind you, the way we define moments are not normalized. Yeah, so you can also define moments to be normalized. If they are normalized, this means that M000 is defined to be 1, right? Or the distribution is already defined to be in integral 1. So, but we have non-normalized moments. So this goes to the power of I, A minus I, M10, M0 divided by 1 by the mass again, B minus J, and M001, M000 by the power of C minus K. By the way, now what is important to see here from this ugly equation is that whatever comes out is a polynomial in the velocities. Yeah? So the higher, so you see that the central moments are functions of the raw moments and the polynomial in velocity. What you should also recognize here is that this polynomial is only in the velocity and not in the other moments. That's a very important feature of central moments, and also what distinguishes them from cumulants. And we'll later talk about cumulants. Yeah. So in central moments, it is completely linear in the higher order moments. Yeah, and non-linear only in the first order moments. That's that will turn out to be important. So I myself always have to remind myself of how this binomial is defined, or I have to look it up. So this is just the a factorial, or I factorial times a minus I factorial. Okay, so this is the binomial, the definition of this binomial. Okay, so now what comes out? Let's look first at 2D. 2D is the case where we have no problems. Yeah. So this is, we come together. If you have any questions, yeah, then please ask. Yeah. So 2D, where we have, for example, K20. So what is K20? If we apply this equation, we end up with M20. So the highest order moment on which the central moment depends is the moment of the same order. Yeah, this is also important to know. Yeah, so the highest order is if we look at K20, then it only depends on 2 moments up to M20. And we'll see that this is now M10 divided by M00. Yeah, so it is divided by 1. Okay, yeah. So why is here a square and not a square down here? So where does this come from? Because this M10 comes from 2 places. Yeah? Okay, up here. Look. Here, this can also be M10, yeah? And then there's another M10 from here, yeah? M10 times M10 divided by M00, right? So this is, but still, you see, this is a polynomial only in the first moment, yeah, in that case. So this now, of course, can be rewritten as M200 minus ux squared times rho. Yeah, this is the moments that we have. And in a similar way, we have K11 is equal to M11 minus ux uy times rho. Right? So what does this mean? This means that, for example, if you look at the equilibrium, M20, yeah, so what is the equilibrium? We know it's ux plus theta, ux squared plus theta times rho. Yeah, so this you should now actually know by heart. Yeah, after listening to this lecture. So there's this temperature in it, and then there is the square of the velocity in it. So basically, you know, if you think physically about this, this is the thermal energy and this is the kinetic energy, right? And they are together in the second moment. So this means for the K20 equilibrium, what is this? This is theta rho because we subtract the ux. Right? So the central moment is only the thermal energy and not the kinetic energy. Yeah. Similar, of course, would be okay. What would be K11 equilibrium? What do you think it is? Okay, so what is okay? Then what is M11 equilibrium? What is M11 equilibrium? Ux uy times rho, right? So and then what is K11 equilibrium then? M11 minus M11 yeah, M11 minus M11 equilibrium. No, not this sounded better. Zero, yeah? It is M11 equilibrium minus this, yeah? And so it's 0, yeah? And this completely makes sense because there should not be any velocity in it, right? So the equilibrium of the central moment should not depend on the velocities. Why not? Because in the frame that we are looking at it, the velocity is 0. Yeah, and so it can only depend on 0 then. Yeah, and 0. Okay, so it depends on 0. What does this mean? The equilibrium of central moments this is not a function of velocity. Okay, because important now is that the frame of reference should in general, not influence the behavior of the method. So this is a general law of nature, yeah? A general law of nature is that the frame of reference in which I state a law of should not influence the behavior of any partial differential equation that describes anything, right? So there is, of course, one thing that we have to one caveat here is the following, that we are now looking at Newtonian physics, and don't consider relativity. So we treat time as universal here, because this would make a difference between Galilean invariance and Lorentz invariance. But because we are even slower than the speed of sound, we are fine with Galilean invariance, even though physically we make a little bit of mistake here. But this is what the level on which we need to understand this. Okay, so in general, this should always be the same. And now we look at whether this actually is the case or not by relaxing. So applying the collision operator of raw moments and look at it in central moment space. Oops. Okay, let's just look at one moment m20 after collision is m20 plus omega 20. So I just now assume all the moments have their own relaxation rate, and this goes into m20 equilibrium minus m20. So this is our standard collision operator, and now the question is the following. If the laws of nature are fulfilled, this equation here should be the same when I apply it to the central moments and to the raw moments. Otherwise, the method is not correct. And this is what we do in MRT. This is just the reminder. In the standard MRT, we relax raw moments. And now let's see whether this is independent of the frame. So what we do in order for this is to replace all the moments that we have here with their central counterpart. So we have, of course, K20, after collision is the moment plus ux square rho. So this is what this raw moment is, equals to now comes on the other hand side, we have the pre-collision state. So this is K20 pre-collision plus again ux square rho plus now omega 20. Now comes the equilibrium. The equilibrium is K20 equilibrium plus ux square rho minus pre-collision state K20 minus ux square rho. So we replaced all the moments by their all the raw moments by their central moments, and the difference is always that there is this velocity square subtracted, yeah, or added now. And because the velocity is conserved, it's always the same. Yeah? So it's always the same, and because it's always the same, we see this here kills this here, and this here kills that here. Yeah. So and then we get K20 after collision is K20 plus omega 20 K20 equilibrium minus K20. So is this good or bad? Good? Bad? It's good. Yeah. So they look exactly the same. Yeah. So one thing that we can conclude, so we could also do it for the other two cases that we still have, but this I guess you believe me, the frame independent for second order moments. Okay, so it's not so which okay, so it's like K20, K02 and K11. So these guys are fine. Okay? So will this continue to third order? What do you think? Third order moments. Unfortunately, we only know after doing a lot of writing. Yeah? So first of all, we have to know what is K20, 221. K21 is M21. So according to our binomial transform, this is minus 2ux M11 minus uy M2 0 plus 2ux square uy rho. So as I told you, it's a polynomial in the velocities, but it is linear in the higher or in the higher than first order moments. Now there is a difference between what we had before, because what we had before was only something like this, which was conserved. And now we have a part that is not conserved because it depends again on moments. So, will this kill our behavior? Okay, again, we have here M11 is K. I mean, we have this guy here and we have this guy here, which we have to replace, right? So this is K11 plus ux uy rho, and we have M20 is M as K20 plus ux square rho. So this we have to plug into it, and then we can solve this for M21 is K21 plus ux K11 plus uy K20 plus ux square uy rho. So this is the result if I express my my raw moments completely in terms of central moments and the velocities. So this we need now to look at what happens in MRT. relaxation in Euler frame. So relaxation in Euler frame means we relax the raw moments m to 1 star is equal to m to 1 before collision plus omega to 1. So each moment its own relaxation rate, m to 1 equilibrium minus m to 1. So unfortunately now we have a lot to write because we have to plug the guy up here. Yeah, we have to plug the guy up here everywhere. Yeah. So and we have to distinguish between the conserved the pre and the post collision state of everything. So this means on the left hand side we have the post collision state. So we have k21 post collision plus u2 xk11 post collision, of course, plus uy k20 post collision plus ux square uy rho, so they don't care about pre and post collision. On the right hand side we have the pre-collision k21 plus 2ux k11 pre-collision plus uy k20 pre-collision. Okay, plus ux square uy rho, so this guy doesn't care. Now comes the thing in the bracket, so plus omega 2. Yeah, now comes the equilibrium part of all of this, k21 equilibrium plus 2u k ux 1 equilibrium plus uy k20 equilibrium plus ux square uy rho. So this was this guy here. Now comes minus, sorry for all the space, k20. So this is again the pre-collision part. ux k11 minus uy k20 minus ux square uy rho. So the thing that we notice immediately is that the guy that was conserved, this is easily eliminated. Yeah? But the guys who are not conserved, they are not so easily eliminated. For them, we have to use the collision operators for the other moments, for example, k20, where we have identified that this is frame invariant. Yeah, so we can say, even though we are relaxing in the Eulerian frame, we can relax the second moment in the Lagrangian frame and have the same results. So this is what we can simply write down, and we have k11 asterisk is k11 plus, and I use different rates for each moment. Yeah, this is not usually necessarily done in reality, but just for the analysis that we make here. So if we use this and introduce this into the above equation, what we come up with is k12 asterisk plus 2ux omega 11 into k11 equilibrium minus k11 plus uy omega 20 k20 equilibrium minus k20, and all of this is equal to k21 plus omega 21 k21 equilibrium minus k21 plus 2ux k11 equilibrium minus k20. 1, 1 plus uy k 2, 0 equilibrium minus k 2, 0. So, hopefully I did not mess up the... Okay, now you have to help me whether I messed up the relaxation rates. No, I did not. I think I did. Did I? Didn't. Okay, this is the trouble if you just write down from your notes. Okay, so let's see, because I'm just questioning whether I'm missing here the relaxation rate. So let's have a look whether what we've actually done. So in here we replaced the equilibrium part and the pre-collision part and separated this out, and there is no, this is correct. Okay, so that's correct, yes. Okay, so let's, in regard of the time, please let me still write me things up. So I hope this will also be okay. So if we now separate everything out, yeah, then we get on the left-hand side k 2, 1 asterisk is equal to k 2, 1 plus omega 2, 1 k 2, 1 equilibrium minus k 2, 1. So this is what we want to have, yeah? This is what we would have if we did it in a Lagrangian frame. And this is also what is in here. However, you also see that there are things, that there are other things. So they come, there's also ux omega 2, 1 minus omega 1, 1 into k 1, 1 equilibrium minus k 1, 1. And I write it here plus uy omega 2, 1 minus omega 2, 0 into k 2, 0 equilibrium minus k 2, 0. And this here is what we call a violation of Galilean invariance. So it's a violation in Galilean invariance more or less for two reasons, you could say. Yeah? The first thing is it is a different equation in this frame of reference and in the resting frame of reference, the Lagrangian frame of reference. This is one thing. And the other thing is when we rewrite it in a Lagrangian frame, it should, of course, be independent of the velocity, yeah, because the velocity is something that does not exist in the Lagrangian frame. This is not supposed to be here. This relaxation in the Lagrangian frame is not supposed to depend on velocity, but it does. We immediately see something else with regard to MRT and BGK. And because you're nodding, I'm now asking you, what is now the problem with MRT in particular that we wouldn't have with BGK?
Maybe related to relaxation time.
Yeah, and what effect does this has in this equation?
If omega 2, 1 and omega 1, 1 would have been same.
Yes, yeah, you see, if these relaxation times are the same, we don't have any violation of Galilean. So BGK does not violate Galilean invariance, right? But MRT does, yeah? So MRT does this by default. So, okay, Galilean invariance, let's write it down. Galilean invariance just means that each law of nature. So I remind you, this is before Einstein, and now Galilean invariance has been replaced by Lorentz invariance. But for what we are talking here, this is sufficient. So each law of nature must be invariant with respect to the inertial means the frame of reference is not supposed to accelerate, right? With the inertial frame of reference in which it is stated. So because in Einsteinian dynamics, of course, the acceleration would make a difference. And also already in, so it would also already in Newtonian, it would also make a difference. So the other thing that you noticed here is that the third order moments, they are not Galilean invariant in the MRT. And now unless, of course, as you notice, that omega 2, 1, 1 is equal to omega 2, 0 and omega 1, 1. Of course, if we link them all together, we lose MRT, yeah? So, but we notice that BGK is Galilean invariant. Now, is this a problem with the discretization? The answer is no, because we have not discretized anything, right? So we did not say, so discretization, you remember discretization of the moment space leads to this aliasing where moments depend on each other, but we did not assume any aliasing, yeah? So there was no discretization assumed. And therefore, it's also not a discretization artifact. So that would be the case even if we have an infinite velocity or continuous velocity model, yeah? And therefore, this problem is not a discretization artifact. Meaning, BGK, no, not BGK, MRT would have this problem all the time, no matter how good you make it. So let us sum this up. So the problems of MRT, we do a lot of MRT bashing here, I'm very sorry, yeah? So the people who invented this are very proud of it, of course. So the ghost moments, they are not independent of each other. even when orthogonal, I mean, with this orthogonal here, I mean the orthogonality that they define, so the unweighted orthogonality. And the ghosts are not Galilean invariant. By the way, this is irrespective of their orthogonality. This has nothing to do, these are two separate problems. So the ghost is not Galilean invariant. So these are the problems that we want to solve. So this is not a problem, both is not a problem of BGK, but BGK is, of course, has other problems because it allows us to have only one relaxation rate. Everything relaxes with the same time scale, which is also not very physically accurate. For example, okay, I did not discuss this here in detail, but what this physically would mean is that the heat conductivity and the viscosity, or the ratio of heat conductivity and viscosity would always be 1, which in reality is not the case. Yeah? And this is the reason for this not being the case is that actually different moments in physics really relax with different rates. And BGK cannot do this because it links all the rates together. So, I mean, both things now don't work, right? MRT, splitting it up, doesn't work, and keeping everything together also doesn't work. Yeah? So we have to think about using a different basis. Yeah. So maybe the idea is that the moments are not the correct basis for MRT, because we are absolutely able to build an MRT with different relaxation rates, where we don't have the combination of the different moments and where we don't have any violation of Galilean invariance, and this is done by using cumulants instead of moments. And this leads us to the cumulant method. So I have a little bit the fear that you never heard about cumulants in any other lecture. Yeah, no cumulants. Yeah. So now we have to make a quick run up through the last 45 minutes that we have in this entire lecture series to get across what we mean by cumulants. Cumulants are not something specific to Lattice Boltzmann method. Yeah, cumulants is a statistical quantities very similar to moments, but they actually are moments, but they are a special kind of moments. And now we ask us, what do we need? Yeah, so the variables, say, I now call them variables to be general. Yeah, with variables I usually mean moments or like velocity and these things. So variables in general the variables we are looking at, they should be independent. Independent, otherwise their relaxation would be coupled. So remember the relaxation. The relaxation is a time scale by which things go to equilibrium. Yeah. Now I thought a little bit about what could this be? For example, think about there is now because we have this war and wheat has become expensive. So yeah? This also means that bread, I mean, at least globally speaking, probably not here. Also, you know that we produce all our wheat ourselves because we are in the European Union and we have a big wall around us. Yeah. So, but globally speaking, wheat is becoming expensive, so bread is becoming expensive. Yeah. So bread, the price of bread and wheat are somehow coupled. So now when the war is over, or there are other reasons why the price of wheat is going down, we would expect that the price of bread would also be going down. Maybe not, yeah, because somebody wants to make money with this, yeah. But there is a part of the bread that is linked to the cost of wheat. So then it may these two things cannot evolve on completely different time scales. So of course, in bread there is not only wheat, there is in particular also the work of the bakery, right? So now what you could separate, if you want to separate these variables, you could say there is wheat, which also adds to the price of the bread, and there is the service of baking bread. Now, if you separate out the service of baking bread and the wheat, yeah, so say you pay, you don't think about paying for the bread in one thing, but you pay for the wheat plus the preparation, and you separate wheat and preparation, then wheat and preparation, they are things that could evolve on different time scales, yeah? But the bread itself is not independent of the price of wheat, yeah? So, you see, the question is, how do you actually identify the variables which are independent, yeah? So now we made this strange thing about, okay, so if I pay here for making the bread and this is not what I actually see on the bill, yeah, but this is the thing that would be independent. We have to think a little bit harder. What makes things? What do we mean with things are dependent on each other, and what in particular means that is independent of each other? So now the question actually, this is more or less a question of definition. Yeah, what are independent? We call these random variables, yeah, because they can, yes, they are whatever random is, they are influenced by some outside things, yeah, like war, yeah. So what do we mean with independent variables? The meaning of independence is that if we have knowledge, so there are two variables, say x and y, and suppose we have knowledge on the state of x. So state of x is price of wheat, right? So you have knowledge on this. Does this implies, so if it's independent, then this knowledge on the state of x implies no knowledge on the state of y. You know, this does not mean that you have perfect knowledge, yeah? So if you know the price of wheat, you don't know the price of bread. But you know when the wheat is going up, the bread is also going up. So this is not perfect knowledge, yeah, but it is knowledge. And the what we mean here is that if you know something about the price of wheat, you don't know anything about the price of vodka. Okay, maybe nonsense, yeah? Maybe there is coupling between these two, but yeah, there should be coupling. I mean, vodka is maybe also made of wheat, as it was very stupid, of cigarettes, yeah? So you don't...
Also coming from Russia, so...
Yeah, it's also coming from Russia, yeah.
More or less.
Yeah, so this is just this is the thing. So when we have two, so the example that we usually have is you throw two dices and you know the one shows 3, then you don't know anything about what the other shows. Yeah, this is independence. This is what we mean. So then we have to derive variables in such a way that they do this based on this objective, yeah, that they separate things that depend on each other. And for this, we have to recall the definition of our moment. So unfortunately, now we have to go in a little bit into the depths by going to the moment generating function. And what was the problem with this? Why this doesn't give us independent variables? So recall the moment generating function. So the moment generating function that we call capital F as a function of capital Xi, which is the frequency of the velocity, yeah, frequency, because this is an usually it's said is an Fourier transform, but I prefer to see it as a Laplace transform. Fourier and Laplace transform are almost the same. The only difference being that we state in the variable that we have a real valued variable in the Fourier transform together with I times real valued, yeah. And here in the Laplace transform, we say we have a variable Xi which is complex, so the I is inside the variable, yeah. So this simplifies our notation a little bit. This is the one difference, and the other difference is that, okay, so there's not difference between Fourier and Laplace, but there's difference between so there's something that you have to take note of, and I made this wrong, unfortunately, in my own papers in the beginning, is that this is actually the definition of the inverse Fourier transform, because there is no minus in the exponent. Yeah, so this is this has the opposite sign convention to the actual Fourier transform. Yeah, so this looks like an inverse Fourier transform. Yeah, and so what we do is actually an inverse Fourier transform of the distribution function, and from this we get the moment generating function. And the moment generating function is a function of is of course a function of the different moments, obviously. Yeah. So this is what is this? This is the probability distribution. F is the probability distribution in frequency space. Okay, so this is pure statistical analysis, actually. Now, the big question: when are variables independent? So the variables are independent. When are statistical variables independent? So you know I mean, you should, because all of you go to machine learning classes nowadays and learn about these things, hopefully on statistics. So what you usually have when you have two variables, you have a joint probability distribution, right? So you have one dice and the other dice, and they are independent of each other. And what is the probability that the one shows 3 and the other one also shows 3? This probability, this joint probability, is the product of the single probabilities, right? So all of you have heard this, yeah? And this is only the case when these two variables are not dependent on each other, right? So we can mathematically express independence by saying that this joint probability function, which is a probability of all the moments, is a factorization. It must be possible to write this as a factorization of single distribution functions for each variable itself. Then they are independent of each other. Yeah. So this is how we get there, and this means we have a factorization. Factorization of distributions. Which means, so our f, which is a function of these variables, yeah, all of them inside here. This is the joint distribution, and it must be possible to write this as a product of the single distribution functions, each related to one of the variables. Yeah? So if we can write this joint probability function as a product of single distribution functions for any variable c, then these variables c will be independent, statistically independent of each other. And now is the question, what are these c's? Because these c's are the independent variables. Yeah, we turned this around. We say this is the property that the variables have. So how do we find them? Yeah. Okay, let me just briefly write this down. So we have if Ci and Cj are independent. So this is the point. Their joint probability distribution will factor. I mean, two factor just means that the entire thing is the product of the parts. Yeah, this is what it means. So now let's see how we get there. So we look at moments, and before we do this, I have to define that this xi, I think I already did this in a previous lecture, this vector xi, we write as its components xi, and here, unfortunately, I never learned proper writing in Greek, so this should be xi, upsilon, and zeta, yeah, capital of these, yeah. So this, I know it looks like a gamma, but there will be no gamma otherwise. So you know what I want to say. So for moments, so how do we get to moments? M, A, B, C, now these are countable moments, are taken from the derivatives. So this is very similar to an the Taylor expansion, yeah, a Taylor expansion of the moment generating function at the development point xi equal to 0. Yeah, this is basically what we have. It's actually not the coefficients of the Taylor expansion, because the coefficients of the Taylor expansion have this 1 over n 1 over factorial n in front of that. This we forget, yeah, but these are still the coefficients of a series expansion without this factor, yeah. So this is why we can rewrite this. So now that the function, the moment generating function, can be written as this series a, b, and c to infinity. Now, as I just said, we have to add here the so these are sets by the power of c, and we have divide to a factorial, b factorial, c factorial, because these are still in the series expansion, and this MABC. So, right, so we can, the moment generating function can be generated the other way around, so inverted, so to speak, by a series of the moments, right, in 3 dimensions in that case. So, and these guys are not independent of each other. So how to make them independent of each other? So for independent, and we call these guys independent. So CI. Yeah? So we are looking for independent guys. And we have the same distribution function. We have the same distribution function, and we say this distribution function looks like this. Yeah, so this is a product somehow to infinity over variables, what's the single distribution functions that depend, each of them depending only on one variable. So this looks different from the above, because the above is a sum and this is a product. Now the challenge is to make from a product a sum. So how do we get from a product to a sum? Looking in the lecture notes. So how do we get from a product to a sum? We take the logarithm. It does not matter which logarithm. Yeah, we just take some logarithm. Yeah, we take the logarithm of this function, and this turns the guy here into the logarithm of the single functions. Now this is now a sum. Yeah? This is now a sum, and this we can relate to this thing here. So now what we define the cumulant generating function as the logarithm of the moment generating function. That's all we have to do. Yeah? That's all we have to do. And then this expansion goes in A, B, C to infinity. And we have xi at the power of A, upsilon by the power of B, theta by the power of C, and of course a factorial, b factorial, c factorial, and c, a, b, c. So this is a small c, this is a large c. Yeah? Or we could also write this inversely as c, a, b, c, because we, of course, we want to compute these guys. Yeah? As the, well, the other way around, of course. This would be zeta c, and we have the logarithm of f c, and we evaluate the entire thing at c equal to 0. Yeah? So taking, again, the Taylor coefficients. Okay, now again, why did we do this? We did it this way because these guys are now designed to be statistically independent, right? Instead of the moments are not statistically independent because they don't have the property that the distribution factors in them. But here the distributions factor in them. So we built in the definition of statistical independence in the definition of these variables, so they'll turn out to be statistically independent of each other, right? Okay. Now what we are doing in the last 20 minutes or so is to look at MRT with cumulant instead of moments, because they should have the properties that we like, and we were missing with the moments. So we'll see, this is, I don't know whether we actually see it, but yeah, we'll also see it. This is Galilean, they are Galilean invariant. And of course, they have independent variables. As we like it to have. So now the theory, nice and good, but looks horrible. Yeah, and actually, in a way, it is also horrible. There's no easy way. I always have to say this in a. So I learned cumulants from a book by Gardinger, and this starts with saying, there is no easy way to compute cumulants. So, how to compute cumulants? We don't want to go through the definition. Let's look at it doing it this way. We want to compute C001, for example, and this is the derivative of in terms from zeta of the logarithm of f for xi equal to 0. Okay, so there is this ugly logarithm. But what we can do is we can apply the chain rule here, right? So, and from the chain rule, you'll see that using the chain rule, we actually get to a way to compute any cumulant, yeah? So because when we apply the chain rule, we apply the chain rule to the logarithm, yeah? So we have the internal, the inner, the outer derivative is the outer derivative of the logarithm is 1 over f, yeah? And then we have the inner one that is dxf. So now magically, the logarithm is gone, right? The logarithm is gone. We just have a derivative of x, f of x, and we know what this is because this is the definition of moments, right? So this is the way moments have been defined. 1 over f. So this is the 0 order 1 over f is a zero-order derivative. F is a zero-order derivative. Yeah, zero-order derivative. We also know what is the zero-order derivative. This is the zero moment, right? And above we have a first-order derivative, so it's a first moment. So this is this guy. Yeah. So this cumulant is this guy, and amazingly, this is U set. And that is sorry. This is not that one. That is 0, 0, 1, of course. Yeah. So this is the velocity in z direction. Okay, look, let's take another one. 2c200. This is the second derivative in the zeta direction of the logarithm of f xi at the position 0. Now again, we have to apply the chain rule. Now we have to apply the chain rule 2 times, and when we apply the chain rule 2 times, we get dz f square divided by f square plus dz second derivative, not z zeta, a second derivative divided by f, and this is in xi equal to 0. And now this here is now this guy, okay, I've written it the wrong way. So this guy here is the second derivative. Is the second derivative, so it's the second moment. Yeah, it's the second moment. So it's the second moment. It's m002 divided by the first moment, by the zero moment, because there's no derivative here. So it's divided by m00. And this guy here is the first moment squared. So it's minus u z squared. And this is something that we already know, because this looks pretty much like the central moment, only that it's now automatically normalized. Yeah? And what we actually have is that if we look at this trace, so the trace is the sum of all the in the tensor of the second moments, the diagonal parts. If you look at these guys here and add them together, because now we subtract the velocity, we divide by density, what is left is the temperature. And now I tell you something that you did not know about cumulants. You guys use cumulants all the time. And our ancestors, thousands of years probably too. Yeah? So first time cumulants were used when a mother told her child when there was a fire, don't touch it, it's hot. Right? So the theory is like, oh God, what is this? But look what comes out. Not momentum, not energy, not nothing abstract. It's the velocity. Yeah? It's exactly what you see in nature. It's just the velocity, and it's the temperature. The cumulants are the guys that you can feel. Right? It's really, really interesting. Yeah? So, because, I mean, it was, think about what mysterious was until the 19th century. What is temperature? What is temperature? Temperature is this cumulant. It's an independent variable. Yeah? This is temperature. Okay, so means first cumulants. First cumulants are velocities. So, and now, okay, this is the trace of second order cumulants. This is the temperature. Now, if you are bored, you can think about whether you can have any simpler thermodynamic explanation what temperature is than to say it's the trace of the second order cumulants. Yeah? So, now we have equilibrium and we have temperature, and the equilibrium of all the other cumulants is 0. I mean, in particular in nature, yeah? So, where there's no discretization and no aliasing and so on. I mean, with aliasing, things may become a little bit more involved. Okay, I have only 10 minutes. I, of course, want to still have some more information. So cumulants in central moments. So what is the relationship between cumulants and central moments? Oops. Okay. Now, in order to see this, we have to make a change in the frame of reference according to the laws of the Fourier transform. You know, every engineer should know Fourier transform in and out and all what it means, yeah, because you need it that often, yeah. So now and not only for understanding Lattice Boltzmann, also machine learning. I mean, you know, nowadays everybody learns this CNN, yeah, convolution neural networks, yeah. They learn convolution neural networks even though they don't know what convolution is, yeah. Yeah, this is convolution. Convolution is a multiplication in Fourier space, yeah. That's okay. So you know, at least you should know these things. And Fourier and Laplace they behave in a similar way because this is different. It's a little bit different nomenclature of actually doing the same thing. So, right. So how do we shift the frame of reference in a Fourier space? This is pretty simple. So if we have an Euler, we have a function, a Fourier transform f, then in a different frame, which now I call just a Lagrange frame, we just move things. So I call this is now a different frame. Now we can move distributions by adding the exponential function u times xi. So this is multiplying by an exponential function. The Fourier transform is just changing the origin. Yeah, and of course you have to remember here that since we have the opposite sign in the Fourier transform, also we have the opposite sign here. So we have the sign convention is here unfortunately different. The opposite to the standard. Just that you are not getting confused, that in the textbook it will be with a minus. And the reason, of course, is when you do Fourier transform backward and forward, the difference is when you do it backwards, there is a plus in the exponent, and when you do it forward, there's a minus. And now we turn everything around and we do backward, forward, and forward, backward. Okay? Yeah. That's all. Yeah. So what does it mean? It means that when we look at things in a different frame of reference, we define this. No, what would I write here? So the A derivative in xi, the B in derivative in upsilon, and the C derivative in from the logarithm of f, yeah, or moved times u times e times u and times theta, and this at theta vector equal to 0. Now, what you will observe here is, because you take the logarithm of this, you can rewrite the entire thing like this. Epsilon b theta c. So we take the logarithm, and here's a product. Yeah, what comes out is u times theta plus the logarithm of the thing. No, not vector. So, and the other thing is we take the derivative, and after taking the derivative, we set c equal to 0. Now, what will happen when we do this derivative? So now there is no u anymore in the logarithm f. Yeah, the only occurrence of u is here, and this will be taken out because it's a linear function. It will be taken out by the first derivative. So the only thing that will depend on the velocity is the first order cumulant, yeah, which absolutely makes sense, yeah, because we said that the cumulants are all independent of each other, yeah. So the first cumulants are already the velocities. That means that all the other cumulants don't know anything about velocity, so they are completely frame independent. All the other guys are frame independent. Now let us write cumulants in terms of central moments. This is what we usually do because this is more efficient. Is more efficient than in terms of raw moments. So Cy. So C002, for example, yeah, this is M002 divided by M000 minus M01001 squared divided by M000. So this is actually pretty simple. So because the cumulants don't care about the frame of reference, they can be written in raw moments and central moments exactly the same way. So if this is the definition of them in raw moments, then completely equivalently, this here is the definition of them in terms of central moments. So now why do I say this is more efficient to write it this way? It is more efficient to write it this way because the central moment K001, Yeah, and for higher cumulants, there are many more of these guys. This guy is 0. Yeah, so now we have some simplification here. When we have a simpler life if we write them in terms of central moment. So by definition, K001 and is equal to K01 and K100, they are all 0. Yeah? Okay, now I'm always running late. But we still want to, I think I still have to say two more things. Yeah, that I just don't want to, you are my hostage now. Cumulant, you're closer to the door than me. I mean, you can just run away if you like. Yeah? We put cumulants to the test. And for this, we recall our problem that we were starting from actually last week. Our problem with the moment M211, right? And here we have either the problem that we had is that we have either extreme overdamping or instability. This could not be avoided with whatever we did in MRT. Okay, so there was of course the one thing that makes us avoid it is, or there were two possibilities to avoid it. One was coupling the relaxation rates, then we are back to BGK, and the other way was to use this special definition of the moment. I have to change this to N211 is equal to M211 minus theta M011. Now let's see what happens if instead of relaxing this guy, we relax the cumulant C211. Yeah, because this should be the one that is corresponding to this. And for this, we of course have to see what is C211. This is actually K211 divided by rho minus K200 times K011. And now there is one thing, even though we are so close to the end, I still have to point this out. We see in the transformation, raw moment to central moments, it was always linear in any higher moment than the first moment. And the cumulants, this is a polynomial in all moments. Yeah? This is now K200 times K011. This never happens with moments, but it happens here with cumulants. Okay? Plus 2K110 times K101, and this divided by rho square. Now the problem that we had is we derived the equivalent partial differential equation at second order. Yeah. So now we have to look at second order because this is where we had the problem. Okay, let's write everything to second order in diffusive scaling, of course. So to second order, this will be K211 to second order, very simple, and this here to order 0, right? Otherwise, this doesn't have any first order, yeah, so this will be 0 order. K200 now to 0 order times K011 to second order. You remember the sums in each term, the sum of all the orders have to be the same, unless you are, of course, you are dividing, then it would be minus. Yeah, so now we have two of them. I remind you, it is an even order moment, so it does not have any odd orders in here. Yeah, only even order, but it has the order 0 and it has the order 2. And so we unfortunately have to get through all of them. So this would be 2 and k 0, 0 to 0 order plus 2 k 1, 1 to 0 order and k 1, 0, 1 to 0 order plus 2k 1, 1 to 0 order and k1, 0, 1 to second order. Okay, now what are these 0 order moments? So the 0 order moments of second order, yeah, so this would be their equilibrium, and their equilibrium would be 0. So this guy is 0, right? We agree. And this guy here, so what would be this? That's theta times rho, right? That is the temperature. So if we plug all of this in here, we get C11 to second order is equal to K211 to second order minus theta K011 to second order, which is exactly what we wanted to have, with the additional feature that, unlike in the MIT world, this is also Galilean invariant on top of it, right? So this solves the orthogonalization problem, and it does not deteriorate in, and it would also be orthogonal in a different frame of reference, right? So the cumulants have solved this problem. So then the last central, the last features. Okay, so the last sentence, unfortunately, for this lecture series is now that we have free choice of relaxation rates if we relax cumulants. Okay, how many? 7 minutes over. Oh, I'm so sorry. Okay, let me see. Thank you for listening, and I'll turn on